Start. So I'm switching to English. So hi everybody. Today we have Boriana Kalderon Asael with us as a speaker for our seminar. Boriana started her academic career actually in Bulgaria, doing her bachelor there, and then moved to maybe I got it wrong. Anyway, moved to Israel to pursue her master's, working with at Huji, working with Yigal Ariel and Uri Dayan on dust sourcing and dust sources, and using geochemistry to trace the sources of dust and relate them to different synoptic systems. Did a project with Enata Aronov and Oded Katz working on landslide dynamics, and then moved over to the East Coast, to Yale, to pursue a PhD working with Noah Planowski mostly on the geochemistry of lithium and lithium isotopes and what they can tell us about the different geochemical cycles on Earth. Boriana recently published a chunk of the result of her PhD in Nature, and I think we're going to hear about that. She's also a mean basketball player, and I have scars to prove that. Right, thank you so much for giving us this talk, Boriana, and take it away.
Thank you for the kind introduction. In fact, I did my bachelor at the Hebrew University in atmospheric sciences.
Sorry about that.
Yeah. So I've been through all of the earth sciences in a way. But yeah, my journey was long, but now I'm going to take you to a different journey into the world according to lithium, or whatever the long title says. I will start with a motivation for this project, and then I'll give you some background on lithium isotope systematics, as I'm acknowledged that not all of us, fortunately, are isotope geochemists. And then I'll elaborate a little bit more on the study itself. I must mention that this is a very large collaborative project. There are many collaborators. I think in the end we were 18 or 19, and I will list all of them at the end of the presentation, but it's a combined effort. All right. Whoops, here. So the Earth as we know it today has experienced a series of icehouse, greenhouse stages. And if we look further back in the Earth's history, this, however, seems to have not been the rule, but rather the exception. The Earth has managed, though, to stay in a clement climate state for most of the Precambrian. What is even more striking is the fact that the early Earth, has had an even harder time to keep itself at this clement climate state, because the solar luminosity was at about 70% of what we experience today. The solar luminosity has increased with time at about, say, 600 million years ago, had reached to about 95% of today's intensity. Still, what is impressive is that theoretically, the early Earth would have been practically frozen. However, there is plenty of evidence that the Earth was not frozen. There was liquid water and sedimentary rocks had formed. So how did that happen? There are different hypotheses and solutions offered to explain a warm early Earth during the faint young sun, or proposing some sort of a cocktail of greenhouse gases in the atmosphere. But for all of those cocktails or mixtures, high carbon dioxide concentrations in the atmosphere seem to be an essential component. And so, in fact, the levels that have been proposed for the Proterozoic are about 10 to even 1,000 times of the pre-industrial atmospheric level. So the key part is that the atmospheric carbon dioxide concentrations have changed with time, which means that the carbon silicon cycle has changed through time as well. So the way that the Earth has managed to keep itself within the freezing and the boiling points of water has been acknowledged to be related to the atmospheric carbon dioxide concentrations. And in order to maintain a close balance between the inputs and outputs of the atmospheric CO2, it is necessary that some sort of a rapidly acting restorative mechanism is operative, such that a rise in CO2 must put into play a process or processes that would work against this rise. And so one key process that has been, that is providing such negative feedback, which also exhibits functional dependence on the atmospheric CO2 concentrations, is the response of the silicate weathering to changes in climate. And the idea is that high global temperatures and especially greater rainfall due to high carbon dioxide concentrations in the atmosphere should bring about an enhanced removal of CO2 via a faster silicate weathering. And the time to reach this new state should take less than 1 million years. This has been calculated by Boriana Kalderon back in 1997. And they also said that if this new state is not reached within this time frame, then it's going to be a runaway effect, and then Earth would end up in either a Mars or Venus-like scenario. So the standard view is the Urey reaction, who back in 1952 postulated that chemical silicate weathering acts as a buffering mechanism to changes in climate. So the chemical reactions that describe the silicate weathering are as follows. Carbon dioxide from the atmosphere reacts with some sort of silicate mineral represented here in a very generalized form, and water to in fact dissolve this mineral, and the products of this reaction proceed to precipitate carbonates and chert. And so the chemical weathering of continental crusts, followed by calcium carbonate burial in the ocean, transfers carbon from the atmosphere to the rock reservoir. So the main point is that there is a carbon sequestration. All right, so that was the standard view, the Urey reaction, but the idea that the terrestrial silicate weathering feedback played a dominant role in climate regulation through Earth's history has been challenged in the last decade. And it has been proposed that sedimentary and hydrothermal processes in the marine realm strongly affected the atmospheric CO2 earlier in the early days of the Earth. And that the reverse weathering in silica-rich oceans helped maintain warm climate through most of the Earth's history. So classically defined as a back reaction that recombines dissolved silica and alkali metal cations, generating acidity in the process, reverse weathering simply describes the in situ formation or orthogenesis of non-colonite type phyllosilicate minerals or clay minerals for simplicity. The main point is that in this process of reverse weathering, CO2 is released to the ocean atmosphere system and could potentially apply another type of climate control. I must mention that this is not a new idea. It has been proposed back in the 60s by Mackenzie and Garrels and Sealand, but then it went out of fashion for a few decades until in the last decade, several groups have revived this idea and started modeling it, the reverse weathering as a climate controlling process. Prominent works are by Christensen, Totten, and Catling. Then Lea and John Higgins' group in Princeton also published a nice work. And in our lab, Terry Eason explored the effect of reverse weathering on the global carbon cycle using a model and suggested that reverse weathering can promote a new stable climate state at higher PCO2 and lower marine pH conditions. He also suggested that small changes in the reverse weathering result in large shifts in the global carbon cycle. It is worth noting that the reverse weathering provides a stabilizing feedback independent of the canonical silicate weathering feedback. The way it works is, let's say we have a higher pH driven by decrease in volcanic outgassing. This enhances the reverse weathering, and as such, it will bump up the CO2 concentrations and lower the pH. And in this way, it's stabilizing the system. And we have the opposite as well. If you have lower pH, this would reduce the reverse weathering because at lower pH, we have more sluggish clay formation. And so high CO2 due to reverse weathering can kind of take on the Fein-Young-Sun. And so things have changed. So we know, there are estimates that Precambrian marine silicic acid concentrations were much higher than what we have today. And one question is, would high silicate concentrations have caused extensive reverse weathering? Modeling work suggests so. And also, did the emergence of siliceous organisms result in a fundamentally different Earth climate state? So the questions, therefore, that I'm curious more about are, how has the silicate weathering changed through Earth's history? And is there a potential that both reverse and continental silicate weathering have changed? And despite the models suggesting extensive reverse weathering in the Precambrian, models are just models. And to me, it's important for them to be verified with empirical data. And here come the lithium isotopes, which can be used to directly answer both of these questions. Because lithium tends to substitute into clay minerals, which preferentially sequester the lighter isotope, lithium-6. I already mentioned that reverse weathering is all about clay formation, but clays can also be formed in the process of terrestrial silicate weathering. The terrestrial silicate weathering can be either congruent, in which the mineral phases are completely dissolved to yield dissolved species, and so there is no clay formation and no incorporation of lithium, so it doesn't change the lithium isotope composition. But there is also uncongruent weathering, which is more prominent today, in which the mineral phases are incompletely dissolved and formation of secondary minerals. And there is a formation of secondary minerals. So I'll expand on the significance of these two modes later, but now I'm going to take a detour and give you some background on lithium. So lithium is a light trace alkali element. It has two stable isotopes, lithium-6 and lithium-7, with the 7 being way more abundant. It is found almost entirely in silicate rocks and is conservative in water, in seawater. The residence time of lithium in the ocean is quite long, at about 1.2 million years, which is way longer than the ocean mixing time. And it means that it is homogeneous in the ocean. The standard delta notation is used to represent the lithium isotope composition, which is the isotope abundance relative to an agreed standard. And we use the LSFEC. That's the agreed standard for lithium, which is lithium carbonate, pure lithium carbonate. The lithium cycle is comprised of two major sources, the riverine and the hydrothermal. The riverine being a function of the continental weathering, congruency or intensity, and thus can vary a lot, while the latter doesn't fluctuate much. The major sink is the formation of autogenic clays in the marine realm, whose fractionation can and should also vary, as we shall see. The delta 7 lithium value of seawater today is 31 per mil, way higher than both of the input values, which implies that the fractionation with autogenic clay formation in the modern ocean is quite high. I would like to expand a little bit on the riverine input. And if you look at the lithium isotope composition here on the right figure, you can see that the range of values measured in the upper continental crust is quite narrow. It's between 0 and 4 per mil approximately. On the other hand, the range of dissolved lithium in river water can vary a lot. So this is a figure from Mathieu Delange's paper from 2015, but I have measured river water samples that range from like 0 to 45 per mil with a mean value of 23. And this is in accord with what I just mentioned in a previous slide or 2 slides ago. When you have a congruent weathering, the riverine delta 7 lithium value will be closer to the upper continental crust because you have a complete dissolution of the primary minerals. But once you have incongruent weathering, then the clays incorporate the lighter isotope, lithium-6, which pushes the residual water to heavier values. And that's why you have this whole range. It's a function of the congruency of the system. So long story short, clays control the lithium mass balance. Okay, so as I said, there are 2 main ways to change the seawater lithium isotopic composition: the continental silicate weathering and the reverse weathering. And here I would like to expand on that. The reverse weathering, in fact, occurs in 2 systems: at low temperature off-axis hydrothermal alteration and in the sediment column. The off-axis clay formation is extensive even today, as it is coupled to extensive weathering of fresh basalts that provide cations and silica needed for clays. However, extensive autogenic clay formation in the sediment column here, where fractionations will be muted, will only be possible in high silica ocean. Today, the ocean is depleted in silica, and there is limited autogenic clay formation, which currently occurs with high fractionation. And thus, the main way for significant change in the lithium burial in the ocean is reverse weathering in the sediment pile. So I'm not the first and I'm not the last attempting to use lithium isotopes as a weathering proxy. One prominent work has been done by Misra and Froelich. They analyzed plankton foraminifera from different places around the world, and they tried to decipher the weathering evolution through the Cenozoic. And they observed this increase in delta 7 lithium values, which they related to the formation of the Himalaya and the weathering related to it. But they also observed this drop at the KPG boundary, which was not the focus of their work and was not that well explained. And this is a special slide for all of the, for Jonathan Harris and all of the foraminifera aficionados. We are currently reviewing Misra and Froelich study with Michael Hinehan, and we are using different types of foraminifera. And so far, we don't see this clear drop, especially not in the benthic foraminifera. But this is study still in process. Anyhow, let's go back. So the foraminifera let us explore the Cenozoic, and then we did a study with Kirsten Washington, testing brachiopods as a seawater archive. They proved to be very faithful and expanded the time window to up to the Paleozoic. However, what I'm interested in is what's happening beyond the Cenozoic and the Paleozoic through the whole Earth's history. And in this case, we could use shallow water marine carbonates. But could we really? And are they a good archive for seawater lithium isotope composition? Well, it seems like they're quite a reliable archive as well. Pogge von Strandman and colleagues in their work from 2019 showed that bulk shallow water marine carbonates can also be a reliable archive for seawater lithium isotope composition. And in their work, they analyzed core top samples, sediments, as well as inorganic aragonites from the Bahamas. And they showed that both have a consistent fractionation from seawater, which was also in line with previously reported fractionation values. And here are Pogge's results. But in general, if I can sum up what's reported in the literature, the fractionation, the factor with calcite precipitation from seawater is somewhere between 6 and 0, while with aragonite precipitation the reported values are between 12 and 8. So in order to confidently interpret the lithium isotope composition recorded in carbonates as reflecting seawater values, we should try to better understand how various stages of diagenesis could affect that recording. And for that purpose, I did an additional work in the Bahamas. It's more sedimentology-based work. I collected a few cores, shallow cores of up to 1 meter, and I divided each core into like 1 to 2 centimeter thick slices, and we sieved them into 6 different fractions and extracted pool water. So I analyzed all these for major trace element, rare earth elements, and lithium isotope composition. But long story short, we see that they all, that the y-axis are not the same, but the message is that they both express their mineralogy-related fractionation very faithfully. So it's a real shallow water marine carbonate seem to be a reliable archive. And then, so what did I do? I analyzed 712 shallow water marine carbonate samples from 101 stratigraphic units that range in age from 3 billion years to the modern. And when I say this, what does it mean? What did I analyze? What did I do? So I know it's a lot of writing, and it might be boring for some people, but some are interested. So on all of the samples, I did a bulk partial sequential leach of the carbonates with a step to remove the adsorb clays potentially, and then it's like 3 stages with very weak acid to make sure that we don't dissolve any siliciclastics that might be present with the carbonates. Then I analyzed all of the samples of the leachates for major, minor, and trace elements. Then I did the lithium columns to separate only the lithium from the matrix. The geostandards that I use are LSFEC, BHVO2, and Atlantic seawater. I measured the lithium isotope composition on the Neptune Plus multi-collector that we have in the lab. And yeah, it's a lot of work. For most formations, we targeted micritic samples. But in addition, we also analyzed some marine cements, microbolites, ooids. We microdrilled those because they show the highest degree of petrographic preservation and the lowest degree of clay contamination. And I also included a few brachiopods in my record. But the important point is that preservation matters. And thus, in addition to the usual petrographic screening, The brachiopods and selected samples were subjected to more exhaustive petrographic examination under cathodoluminescence microscope, or CL. I cannot pronounce this word. So these images over here are from the CL microscope, and in general, the yellow the samples appear, the more altered they are. So we had to omit them. And here on the top, this panel of 3 images is from brachiopods, just to show different degrees of preservation. What you want to see is this deep blue color on the CL, which indicates a pristine sample. But then in most cases, you do have some degree of alteration, and this is just the garbage. If you see this thing, it's just run away. And at the bottom are also microphotographs of well-preserved Paleozoic carbonates. And this is the new carbonate lithium isotope record through the Earth's history. On the x-axis is shown the age of the samples. On the y-axis are the delta-7 lithium values measured in those samples in per mil units. The closed symbols denote all of the published data so far from carbonates, and the open symbols denote my contribution to the record. And as you can see throughout most of the Earth's history, the delta-7 values range between 0 and 15 per mil, with an average of around 7. And sometime in the early Phanerozoic, a shift occurred. And you can see that there is a clear transition of the lithium isotope base value from around 7 up to around 20 per mil. So the lithium isotope value of carbonates, and hence seawater, has changed significantly, indicating that different weathering processes were in charge. But how can we be sure that these carbonates record a primary signal and not an overprint? That's a major issue, and I've done my best to address this. I cannot be 100% sure though. What I did, as I said, I added some marine cements, very well preserved marine cements. I filtered my data according to major, minor, and trace elemental ratios to gauge the effects of mineralogy and diagenesis. And I also focused on carbonate units that are not from carbon isotope excursions, because they are either short-term carbon cycle perturbations or diagenetic events. And this is not what I'm interested in. I want to know how the background value of evolved. And I also did some calcium isotope analysis on 6 Precambrian stratigraphic units, because potentially if you see correlation between the calcium and lithium isotope units, it might indicate that there is some diagenetic trend in those samples in these units, and we don't need them. So if you worry about the low delta-7 lithium values in the Precambrian being a result of diagenically altered samples, then Ullman's study on Jurassic belemnites had shown that diagenesis would, if anything, drive the delta-7 lithium values to higher values, which is similar to what we know about strontium isotopes in carbonates. And that's the main reason why we use a fit through the lowest strontium isotope values to learn about the seawater strontium isotope composition evolution through time. Sorry, my dog is here. If you look at the rubidium-calcium ratio used for filtering of detrital material and contamination, you can see that practically all of the samples had rubidium calcium ratios lower than 10 to the -5, indicating no detrital contamination. And still the trend persists. Similarly, if you look at the manganese strontium and manganese calcium ratio used for diagenesis, most of the samples have very low ratios, indicating for the most samples that they have not undergone any diagenesis. And there are two scales, one for lower values and one for very high values. And as you can see, the ratios are elevated as we go back in time. But this is expected since the Proterozoic marine manganese concentrations were much higher due to the widespread marine anoxia. And still the trend persists. I must mention that the Phanerozoic samples in my record were filtered by the accepted manganese calcium ratio, but this is not applicable for the older samples, as I just explained. And then aluminum calcium ratio, of course, indicates a siliciclastic contamination, and I applied a reasonable filter. And you can see that the trend still persists. So it must be a real trend. The calcium isotopes, as you can see, there is no specific trend in either of those formations. So I cannot, it doesn't signify or indicate any diagenetic alteration in those units specifically. So after applying all these filters, here is the screened new record. It's just my data this time without the published. The lower delta 7 lithium values throughout the Precambrian gradually transition to higher values in the Cenozoic Mesozoic. The solid curve represents the lowest fit through the mean delta 7 lithium values, and the dashed one is again the lowest fit, but this time through the lowest 10% of the data, similar to strontium. Because if we have successfully filtered for detrital contamination, both with rubidium calcium and aluminum calcium ratios, which is the one that would bring to lower values, then any potential undetected diagenetic alteration would bring to higher values. That's what we know, at least today. So the fit through the lowest values should be the more representative of the seawater lithium isotope evolution. This trend is very similar to a first order approximation to the trend observed in carbonate oxygen isotope record. This one, which is curious. And here is just yet another representation of the same data, just beamed for 4 major geological periods. Still, the Cenozoic Mesozoic is significantly different than the rest. So we have this clear transition in the record. How can we explain it through mass balance? Well, as I said, it's all in the clays. As I said, formation of clays controls the lithium isotope content, and thus riverine input and the autogenic clay formation output are the ones that can change a lot due to different weathering regimes. And this is what the lithium mass balance look like today. On the left, it's slightly different from the one that I showed at the beginning. It just incorporates the Coogan's low temperature hydrothermal alteration estimates. While on the left is the Precambrian one, which we calculated. On the right, I don't know what I said. According to the data set, the Precambrian ocean had low delta 7 lithium value of around 10 per mil. And how is that obtainable? So we can learn from the mass balance model that in order to get such low values for the ocean, we need to change both the riverine input value, which must be much lower at around 5 per mil, indicating more congruent weathering. And the fractionation factor with clay formation in the sediment column must have changed a lot. It must have been practically muted. So this is the formulation of the mass balance model. We assume steady state, since we are interested in long-scale processes. We followed Lee and West lithium isotope mass balance, but we also adapted the parameterization from Caves and Rugenstein, which captures the dependence of the lithium flux on the riverine isotopic composition. So we solved this model at 1 million year intervals. We used a Monte Carlo resampling approach for key parameters, including random combinations of almost all of the fluxes and isotopic values. And we ran this model 1,000 times at each time step, so that we can determine the most likely solutions for our empirical record. Yeah, that's kind of a complicated slide, but we used as an upper and lower bounds our lowest smoothed delta 7 lithium record with an applied calcite fractionation from seawater, and then to be more conservative as possible, we set the lower bound to be at -4 per mil in case there are buffered conditions, and the upper bound we set at +5 so that we can capture any samples expressing aragonodic fractionation. All right, so I would like you to focus mostly on panel B and panel D. Panel B is the delta 7 lithium of the riverine input. And you can see that in order to satisfy the empirical record, these values must be very low throughout the Precambrian, and then they shifted to higher values. And similarly, the fractionation factor with clay formation in the marine realm, in the sediment pile, must have been very low, almost muted throughout the Precambrian, and then it switched to higher values. So in order to show how high sedimentation rates can affect the lithium isotope fractionation, I applied a steady-state diffusion reaction model proposed by Clark and Johnson, which is a modification of Johnson and DePaulo's model. And this model examines the dependence of the effective fractionation factor on the depth of the non-reactive zone. Maybe I should explain the difference between effective and intrinsic fractionation factor. The effective fractionation factor is the one that expresses the weaker isotopic fractionation observed when the system is not homogeneous, and the measured reactant pool is not in intimate contact with the reaction sites. While the intrinsic fractionation factor is the full fractionation that can be expressed, which is when the system is homogeneous. Lambda is the dead scale for penetration into the reaction zone. It's also called the e-folding distance for concentration decrease. D is the diffusion coefficient, and K is the first order reaction rate constant. And here are the results. On the x-axis is, in fact, the effective fractionation factor with clay formation in the marine realm, the autogenic clay formation in the sediment pile. And on the y-axis is the first order reaction rate constant. The different lines are the just different intrinsic fractionations that we observe today. They range between 15 and 25 per mil. The two colors, the black one represents, they're just two different e-folding depths, with the black one representing shallow marine conditions, and the gray one, the deep ocean with slower sedimentation rates. And so if we have higher silicate ocean, which would promote higher rates of clay formation, this is also represented by the first order reaction rate constant, then you can see that it is quite easy to get more muted lithium fractionation if we have higher rates of clay formation in the marine realm. All right, so what did we learn from this whole exercise? The input value alone will not explain the long term. The reverse weathering must have also changed. Lithium isotopes track the extent of both the reverse weathering and the terrestrial silicate weathering, but more reverse weathering would result in lower seawater lithium isotope values. So here is our evidence for change in weathering regimes. What could have caused this shift, though? So let's start with the input, or the riverine lithium isotope composition. Well, the proliferation and the diversification of land plants over much of the Cenozoic has been hypothesized to have fostered more extensive formation and retention of clay minerals in the terrestrial realm, and our work, I think, supports this idea. There are multiple ways in which plants may have changed the weathering, but I think that fostering soil development and increasing the water-rock interaction times is one way to increase the probability of clay formation. And in the marine realm, well, extensive clay formation in the marine realm, in the marine sediment column, has been proposed already for the Precambrian, and it's one obvious way of changing the marine lithium cycle. So for the majority of Earth's history, without the presence of silica biomineralizers, seawater was highly oversaturated with respect to silica phases and clay minerals, which could have resulted in rapid and extensive clay formation. The progressive decrease in the marine silica concentrations over the Phanerozoic could be linked to the transition to more biologically controlled silica cycle. And this may have driven the shift that we see in the lithium isotope values. So to conclude, the carbon cycle seems to have operated in a fundamentally different mode for the majority of Earth's history compared to present day. There was a major shift in the clay factories through Earth's history, increase in clay formation on land and decrease in clay formation in the oceans. The shift from Precambrian Earth state to the modern state can likely be attributed to significant biological innovations. And our record suggests that this development of a more modern-like style of carbon cycle is tied to these ecological transitions, and it was a protracted one, a more gradual one, rather than being marked by a step-like change. So I would like to acknowledge the contribution of all of the collaborators and the people that I'm still working with, as well as the financial support from NASA, NAI, and Packard Foundation, and of course, the department that I work at right now. Thank you for your attention.
Right. Thank you so much, Boriana, for an awesome talk. And questions, if you have a question, just unmute yourself and ask. If not, I have like a billion questions, so. Okay, I can get us started. So I was wondering, I mean, you obviously worked very hard to really target the best preserved fabrics. And my question is, did you just try and analyze a bad fabric, something that is obviously metamorphosed or diagenetically altered, and is it really off in its lithium isotope?
Yes. So not metamorphosed. I mean, I didn't use any metamorphic samples, but if you note here in the unfiltered record, these guys with almost 70 per mil samples, these were diagenetically altered brachiopods. So they're like extreme values that, that don't make sense.
So what can you tell us what happens during diagenesis that drive the lithium isotope composition up by 40 per mil?
I don't know how exactly, but you have different altering solutions that pass through this area, and they modify. It could be also potentially solutions with different temperature, or it could be just different different composition. But
I mean, I'd expect higher temperature to result in a lower fractionation factors, right? Which will kind of lead me to my third or fourth question. But I'm just curious. I mean, one way to explain it is if I don't know, it's either source or process, right? Like you need to remove some isotopically light lithium to somewhere else. You need to mobilize it.
Yeah. I don't know. I don't see this expressed anywhere so far. There are other very curious examples, but we can talk about them.
Okay. No, it's really just super interesting stuff. Another question.
Yeah.
You've shown that or you suggest that both the lithium composition of output of rivers is decreased, and the isotope fractionation for orthogenic clays, marine orthogenic clays, is also lower.
Yeah.
And if I understand right, your explanation for the latter is that it's some kinetic effect related to faster.
No, it's a diffusion controlled process.
Yeah,
because if you have high sedimentation rate, lower.
So you're not expressing the full, equilibrium fractionation factor, right? Yeah. But another explanation would be elevated temperatures, and people have suggested that Archean oceans. I mean, it's a huge debate, but some people suggest that the Archean Ocean were like 80 degrees centigrade, or much warmer than the present. So I would like you to comment on that.
Yes, sure. So we didn't play with the temperature, but we did play with different outgassing models, because there are plenty of those. Here, the one that I showed and was also showed in the main text in the paper is the one that was proposed by O'Neill in Holland and Tajiki and Matsui. But we also tested with the Korenaga constant outgassing, and with Fuentes curve as well. And we played with this. If you look at the sediment, at the supplementary, you can find all of them. like different ranges of the parameters, but it's still, this is, because this one is the most accepted one, we use this one, and these are the results.
Yeah, so I guess my question is, if you wanted to explain, I don't know, 8 or 11 per mil difference in the isotope fractionation factor by temperature, how high the temperature of the ocean should be?
Now, this probably can be calculated with the diffusion coefficient, because I know that the diffusion coefficient, or the ratio between D7 and D6, varies with temperature. And if you have higher temperature, then the ratio becomes significant.
I'm sure that people, try to just precipitate clay in a reactor at different temperature and look at the...
Yeah, so people that work in on off-axis alteration, they have already done plenty of studies and show the dependence of the diffusion coefficient with temperature, but it has been shown that for in like environmental conditions, as we know, on the surface of the Earth, they're practically 1. The ratio is practically 1.
Okay.
So.
More questions? Anyone? Okay, I think, Boriana, that you are off the hook. But I'd like to thank you again for an awesome talk. I learned a lot, and I will definitely look at the supplementary file.
Yeah, it's in this kind of papers, it's like 2 pages of a paper and then 42 pages of supplementary. More the work is there.
I said I look, I won't read it.
Yeah, scan the figures. Thank you.
תודה רבה.
תודה לכם.
Bye.
Bye bye. How do I get out?
אני הולך לחתוך את כולנו.
טוב מדי. ביי.